Okay, let me start with something which is very elementary and very, I would say, transparent, but still there are some doubts. Students develop some doubts because of notational difficulties, notational differences in different books. I'll start with the most fundamental difference. In scientific literature, you are used to write this temporal factor as e to the power minus I omega t, as opposed to this is your scientific. Oh, okay. Generally write smaller ones. So in science, this is the biggest I can achieve. Is it okay? Okay, you will be writing the temporal factor as e to the power minus I omega t. Monochromatic waves will be writing like this, whereas the engineering community, they will be writing e to the power plus j omega t. This simple looks very simple, but then it creates a lot of confusion. First consequence is that you talk about a polarized light, you talk about right circular or this left circular polarization. It depends on your viewpoint. That means you can have two different kinds of viewpoints. One is the source viewpoint, other one is the detector viewpoint. If you look from the source, that means you are looking from source and the light is going this way in this, let's say, z direction. So if you have a right helix, it is your right circularly polarized light. The tip of the vector rotates in a clockwise direction, you call it the right circularly polarized. Now if you go to this kind of notation, the same thing will be a left helix. So this will be looking like this, light is rotating like this, because right helix from the other side, from the viewpoint of the detector, it will be left helix. And hence right and left, they will be differently interpreted, and again origin is like that, how you write the temporal factor. Okay? Now this is sidetracking a little bit. Let's say you are doing Fourier transform. You are using, many of you use this MATLAB. I burnt my fingers for a couple of months to understand this basic thing, that you write this forward transform, you will be writing this e to the power minus I omega t, temporal transform, the temporal factor. E omega you will be writing Ex e to the power Et. If you are taking this forward transform, you will be writing Et as integral and then E omega, which is the spectrum, and e to the power minus I omega t, and then d omega. That's the way you will be writing. But this forward transform, if you have this kind of, they use this, MATLAB uses this convention, this forward transform, for us it will be a backward transform. So forward and backward transform, they get mixed up in this if you are not aware of this problem. So you may think that you are doing forward transform, but practically what you are doing backward transform. Okay? Anyway, and the other thing, this is one thing. So this point, if you write this right circular polarization in this convention, you will be writing right circularly polarized light, these components as this is 1, and then minus I, this is RCP, and the LCP you will be writing it as 1 by root 2 in Jones representation, 1 and plus I. Okay? But this is not from source, this is a source viewpoint. In detector viewpoint, it will be writing the other way. RCP will be writing 1 plus I, and then other one will be 1 plus minus I. Okay. This is one comment. And other comment is, nobody mentioned till now, I was observing carefully, people are not mentioning the standard things about polarization. I mean, it is obvious, perhaps people think that, they assume that things are all known to the students. So let us first start with the scalar wave. Let's say you have a scalar wave, which is a function of spatial coordinates and time. So you'll be writing, let's say I take this electric field, or first take the scalar wave, so it is x, y, z and t. You'll be writing the 2D Fourier transform as dkx, dky. Of course, there is a double integral e to the power this e, this is kx, ky, and then z, and then e to the power I kxx, e to the power I kyy, and then e to the power I kzz, okay, and then minus omega t. Okay, so that's the 2D Fourier transform of standard scalar wave. Now here, look at the structure of this kz. Of course, this kz you can recognize that kz will be the square root of k square. Let's say you are talking about free space propagation, the wave vector will be the wave vector omega by c, free space wave vector. This is k square. If you have a refractive index, it is medium having refractive index dielectric function given by epsilon. You'll be writing like this, or you can, if you have non-magnetic medium or magnetic medium, you'll be writing epsilon mu, and then k naught square epsilon minus kx square minus k square, ky square. That's the way we'll be writing the z component of the wave vector. Let's forget about this medium. Let's take, I'm talking about free space propagation. If that is the case, you look at the structure of kz, you learn the fact that only inside a circle of this radius k, that is radius k naught, inside this circle, you are having this kz real. Okay, outside this kz is imaginary. So this thing is only inside this circle. Here I am plotting this kx, here I am plotting this ky. This just tells you only with the small cone from the main direction of propagation, wave remains propagating, and beyond that, all outside this whole kx, ky spectra, you will look at the spectra, all of these parts, they are evanescent. So that's how you learn that this, your major part of the spectrum is all comprises of the evanescent components, and then this inside this circle you are having these propagating waves. This lesson I'll be now mentioning now and now. Till now, most of the lectures were concentrating on far field effects. They are not dealing with these evanescent waves, but I will be trying to show you that evanescent waves in the near field, they play a very important role, and they are the ones who decide the nature of physics, which you will be having inside in a small objects where you are bound to encounter these evanescent waves. So we need to be alert about those things. And I'll show you, you are used to interference effects with propagating waves, but this near field evanescent waves also, they can destructively and constructively interfere. And that's the consequence which leads to the spin locking and spin direction locking. I'll come to more details. I'll be detailing the experiment which was done in 2013 by this King's College group under Professor Jayatz, okay? I'll be detailing the details of that experiment so that you can understand the nitty-gritty of this process, how important the role of these evanescent waves are, and how they affect the dynamics of the optical phenomena. Okay. Now, another thing as I go along, I'll be discussing this evanescent waves, which will be specializing to the cases where you have this evanescent waves and then you have under this total internal reflection. So usually the kind of boundary value problems you solve in this class of problems, let's say you have an interface, this direction, let's say z direction, this is your x direction, this is your y direction. Let's say this is the interface of the medium. So z is equal to 0, that gives you the plane of the incidence. Now let's say you are coming in with a wave here with this at an angle theta. It's a propagating wave coming from free space falling on a medium with this here is epsilon, this n is equal to 1, n is equal to 1, n is maybe greater than 1 or something. You know you'll be having refraction and other effects. Now if you have a situation that this epsilon 1 and epsilon 2, epsilon 1 is greater than epsilon 2, then you'll be having the possibility of this total internal reflection. You cross this total internal reflection, then you'll be having this energy will be propagating backwards, and then you won't be having anything in this, no energy propagates in this direction. But if you look at the structure of the wave, you learn that waves are evanescent here. As you go away from the interface, the wave amplitude decays as a function of the transverse coordinate. it gets reflected in the fact that whatever wave vector you talk about is now essentially complex in nature. The propagation direction, this x component is going to be real, but then this component of the wave vector, z component of the wave vector is bound to be essentially imaginary in character or complex, in general complex in character. That's what tells you that wave, as they propagate in that direction, it is bound to decay as you go away from the interface. That's the character what you have. By the way, since I'm mentioning this thing, this evanescent tail, and then I must mention Sir J.C. Bose's contribution in this regard. So this electromagnetic tunneling he discovered in the language, but this is the same thing you have as in quantum mechanics. So let's say you have two prisms, there is an air gap between these two prisms, light falls like this, it gets totally internally reflected. Now here of course the tail of the evanescent tail, if it is closed, this other prism is close by, it can tunnel through, it can go out over here. But if you make this distance large, which is larger than the evanescent tail, further away from the interface, then you will be having a situation light doesn't pass through. So this is your standard electromagnetic tunneling through this thing. This is Sir J.C. Bose way back in 18th century, end of 18th century, he did some classic experiments in Kolkata, and he showed this thing. So this is the essence, same thing what you have in case of standard quantum mechanical barrier. So far as 1D problems are concerned, you cannot distinguish optical problems from your quantum mechanical problems. Electromagnetic tunneling phenomena is exactly the same thing what you have in case of this barrier tunneling. Okay? Because here, the waves are going to be, if you come in with this energy which is lower than this height, here the waves are propagating, this is propagating waves, here the waves are evanescent, here again the waves are propagating. So that is mimicked by this thing, you will do this thing. And the way you handle these problems, boundary value problems, that's very simple. What you will be writing, for this medium 1, you will be writing some A1 amplitude e to the power I K1, let's say this is K1Z, and then e to the power I K1ZZ and IKXX. Okay, that's the way, this incident wave in, and then plus A reflected e to the power minus IK1Z, and then Z, and then this thing, I think you can write it in this thing, e to the power IKXX. That is your E1, okay, this EY1, and then same way you can write this expression EY2. In the second medium, there will be outgoing waves, you'll be writing as e to the power IKXX, and then AT e to the power I K2Z, Z, and then there is nothing like here. Of course, this temporal factor is also there. Now what you do, you demand that the Y, this component is tangential across the interface. You can calculate the magnetic field, corresponding magnetic fields by using the Maxwell's equation, and demand that X component of the electric field also continuous. This gives you two equations. This thing is known to you, incident amplitude, you can find out what is this AR, what is this AT. Other thing you remember, this Kx is the surface component of the wave vector that is also continuous. That's the reason I am writing the same X component of the wave vector, tangential component of the wave vector for both these waves. Okay? Now, if you look at the structure of K2Z, that will be your K naught square epsilon 2 minus Kx. Kx is, of course, this Kx will be your K naught square epsilon 1 sine square theta, because you take this component, surface component here, it will be K naught square epsilon 1 sine square theta, because the wave is incident from this medium E1. Now, the moment this quantity crosses 0, earlier it was real, now it becomes purely imaginary. So that means the moment you cross this theta crosses this theta critical, you encounter the case of total internal reflection. Waves, do not think that wave doesn't penetrate at all in the second medium. It does penetrate. And that's the reason waves has a character which is evanescent. So I'll come to more details, exact expressions for these waves later, at a later stage in one of my slides. Let's now get going. Okay. So now let me start my lecture with a brief plan Of course, not everything I put down on this slide. So I'll be starting with simple transverse plane wave, okay, that everybody is familiar with, just to make you aware with the notations which I'll be using. Now, what I mean by helicity, though it was mentioned so many times in many other lectures, Nirmalya did that, many other speakers also did that. So I'll be starting with the simplest possible, sorry. So I'll start with this transverse plane wave first, then pointer is sent? Yeah, okay. So transverse plane wave, then I'll show you this, this transverse plane wave can be of two different characters. One is the homogeneous wave, which is a standard propagating plane wave in free space, or in presence of boundaries, there you'll be having this so-called, you may encounter the evanescent waves also. Then I'll show you there's some similarity between these two if you talk about these plane waves and this thing, because in both the cases you can structure the beam. The moment it is evanescent is already you are dealing with inhomogeneous wave, and there is a structure in the light. Okay, so they have some common grounds to share, and that's how some genetic effects you can talk about, which will be shared by both these cases. In case of transverse plane waves and these Gaussian beams, you will encounter the same kind of physics. Okay. Then of course I'll be concentrating on the evanescent waves, how it happens in total internal reflection, or when you excite this so-called surface plasmons or this localized plasmons, what will be the character of these evanescent waves and how it affects the light phenomena. Okay. Now finally I'll be talking about the structure of the Poynting current, which was a seminal paper by Michael Berry in 2009. So I'll be detailing some of the details of that thing, because that whole paper is part of it is about scalar waves and part of it is vector waves. And Berry, the point he was trying to drive in that paper is that the features what you derive from scalar waves can be much more simplified compared to the actual scenario when you have to take into account the actual vector character of the wave. Okay, so I'll be spending a lot of time on this Michael Berry's paper and establish the connection with quantum mechanics. Okay, I'll do that. And after that, I'll show you this. If you talk about spin has also a very interesting structure when you give a structure to your beam. Okay, so that thing I'll be spending again a lot of time. And only two experiments I'll be discussing in my lecture. Both are seminal experiments. One was done in 2013 by Jair's group, which I said, and the other one was done in 2016 by this Riken group, in Franco Nori's group in Japan. Okay, both are seminal experiments. So those two path-breaking experiments I'll be detailing in the lecture. Okay, and I'll show you this transverse spin momentum. Transverse spin momentum is a tiny effect. In order to measure that thing, you need to have a resolution of your device so that it can measure these forces of order femtonewton. The resolution has to be order of femtonewton. Effect you have, that is order of piconewton. Think about that, 10 to the power minus 12 Newton is a tiny force. So that was the so-called Belinfante, who was the originator of all these notions. He used to believe that this is elusive and you can never measure it. So that's the reason he said it's an elusive kind of thing, you can never measure, but it is there. In order to retain the gauge invariance in field theory and gauge invariance in electrodynamic theory, you need to retain this transverse spin, and otherwise your system, your mathematical structure breaks down. So that was a seminal paper by Belinfante, and that was in 1940. Experiments on these tweezers. He'll be talking about those things after my lecture. Okay, now since we learned that this force is so tiny, it's of the order of piconewton, and this 0.5, 0.6 piconewton, then you need to think about ways and means how to enhance this effect. So we could chart out several areas. It's mostly our research work, but then I'll spend little time on them. But I'll tell you the spirit. One is you can use the strongly coupled system. Gopal may talk about much more that, not in the context of spin optics, but in different contexts. He'll be talking about strongly coupled system. I'll be giving you the basics of the strongly coupled systems. And I'll show you when you have this strongly coupled system, you have the so-called phenomenon of avoided crossing. It's genetic. It can happen in atomic physics. It can happen in standard optics. It can happen in any areas. Let's say you recall the chapter of the small oscillations in Ghost's book. You understand this thing, very genetic features of this phenomena a very average scale. Okay. So then I'll be talking about something which is known as the coherent perfect absorption. There's a lot of noise about this anti-laser or something. And this kind of things, strongly coupled systems or coherent perfect absorption mixed together, they can lead you to very strong field enhancement. And that is quite, you can regulate where this field enhancement will be there because you're dealing with resonances. You have enough handle to control the resonances, the location of the resonances, the width of the resonances. So all these parameters you can control. So you exercise those freedom, those degrees of freedom to encounter a very strongly enhanced field. And that enhancement, of course, leads to the strong enhancement in the spin orbit coupling. Okay. So I'll be talking about some of that. And then finally, this is again a very theoretical proposal. You can use the exceptional points in PT-symmetric systems. You talk about a PT-symmetric system, many of you know that this is a very interesting class of problems where you have a complex Hamiltonian, non-Hermitian Hamiltonian, but still allowing real eigenvalues. So you are used to the fact that if the Hamiltonian is Hermitian, your all eigenvalues are real. You can construct your Hilbert space. You can construct your orthogonal set of vectors. You can have a whole full formulation of quantum mechanics, but all based on real eigenvalues, so that your original Hamiltonian is Hermitian. But it turns out that you can have these generic complex Hamiltonians where this PT symmetry is there. Your time reversal symmetry, parity symmetry is there, and if this symmetry is retained, then you can have a region where you can have all the eigenvalues real. The same kind of story that you can still have real observables. So there was a guy, Mustafazadeh, in Turkey. He did a lot of work, seminal work on this thing. He would show that you can talk about these PT symmetric systems where you can have this so-called the exceptional points. You look at the structure of the scattering matrix, and if you look at the structure of the scattering matrix, so the Green's function, simply the Green's function of the structure, you find that there are poles in the Green's function, and those poles lead to infinite growth of the both reflection and transmission. So those points where this thing happens, you call them the so-called exceptional points. And near this, you can exploit these exceptional points to enhance this transverse spin. That is, again, as I said, is a theoretical proposal. We did some calculations. I could show you that how this transverse spin effects also can be enhanced by many orders of magnitude. Instead of piconewton, you don't need to have that kind of accuracy. With much lesser accuracy, you can measure this transverse spin momentum effects. Okay, so let us get going. So let us start with the simplest possible case. So the way you will be writing a standard transverse electromagnetic wave, of course, I am not writing the temporal factor anywhere. As I said, it is e to the power minus I omega t. So look at the structure. You go to Born and Wolf. Born and Wolf defines this polarization like this. By the way, let me make a comment here, which is maybe is not paid much of attention. When you talk about polarization, Born and Wolf defines a quantity P, which he defines at EY in phasor notation and then by EX. So let's say you are having a wave propagating in the Z direction, and this divergence of E is equal to 0. That tells you the wave is bound to be, so for as free space propagation, this electromagnetic waves is bound to be transverse in character. That means electric and magnetic fields must oscillate in the plane transverse to the perpendicular to the direction of propagation. So E and H must be in this plane, in this XZ plane, XY plane, and the wave is propagating K is in this direction. Now, in phasor form, I'll make another comment about these phasors later, because that is again a source of confusion amongst at least my students I have encountered. So this is a big source of confusion later. I'll talk about that later. So, but the Born and Wolf defines like this. But the main point I would like to point out here, this polarization is a concept developed for plane waves. But when you talk about beams, it's a totally different kind of structure, totally different kind of scenario. I'll talk about that with beams because in that case, and then this one, if you talk about beams, as I just now said, that this E, R, and T, you'll be writing it like this. So in the scalar form, I was writing as dkx, dky, and then e to the power I kxx plus kyy, and then plus kzz. Okay, and then I'm not writing the temporal part here, so let's forget about that. We know all that things. So and then E, Kx, Ky, Kz. Sorry. Okay. Now let's say this is a scalar form. The moment in many literature you see in current literature, you will be writing the Gaussian beam and everything in this. You call this thing Weyl representation, W-E-Y-L representation, or angular momentum representation. So that means if you have a beam, let's say you have a Gaussian beam or something, it's basically in K space, it is a spread of wave vector along this certain KZ direction. There will be different wave vectors propagating in different direction. The moment these transverse components become large, this quantity, this Ky and Kx become large, this Kg can become complex, which I already discussed, right? So for larger these transverse components, Kx and Ky, waves become necessarily evanescent in character. But then you need to, for actual rigorous treatment, you need to retain all these transverse components, and hence you are bound to include these evanescent components in that. Now let's say I want to talk about a vectorial theory. What people do in many of the literature, what they do, they will put just some Ex, Ey, and this thing, they will be putting it like this. So they transfer this Gaussian beam, they will say, okay, this Gaussian beam is having this Weyl representation, angular spectrum representation, and you can write an overall vector direction for this thing. But that is not, I would say, that is not correct. What this Debye and Wolf, they developed a technique where you, at this stage, you separate out both this TE and then TM polarizations. So one is referred to as the S polarization, other one is referred to as the P polarization. And the way you do it is the following. Let's say you have this interface, and this is this interface. So this is this normal to the interface, and the wave is propagating this way. So this K is like this. So this direction K and the normal to the interface, that defines the plane. That is what you call the plane of incidence. So now everything happens in the plane of incidence. That's not the case if you have this meta surfaces and other things. That's a different business. If questions are there, I'll focus on that. So now the question, so what do you do basically at this stage? You separate out the TE component. So TE component and the TM component. That's the so-called Debye-Wolf representation. Many of the students in IISER Kolkata under Oyon and Nirmalya, they did a lot of work along this kind of decomposition. Okay, so some of the posters also have that thing. So okay, so that's the way you avoid this thing. So, but remember that the main concept in this, if in phasor notation, both this EY and EX, they are complex quantities. This ratio determines. Now, this quantity, if it is real, that means EX and EY, they are having the EX and EY, they are having the same kind of character. Either they are both real or they are both complex or this thing, but the ratio is real. In that case, you have this so-called linear polarization. If this quantity is complex, let's say plus minus I, it is plus minus I, you have the so-called circular polarization. In one case, right circular, other case, the left circular. And if it is just any arbitrary complex number, alpha plus beta I, in that case, in general, you have this elliptically polarized light. So, but in standard scenario, you can summarize all that. You can write this wave like this. So this is X component, this is a Y component. This M is a factor which is related to the helicity of the beam. The imaginary part of M is 0. That means the helicity is 0. That will correspond to either X polarized or M is real. In that case, this will be X polarized or any arbitrary polarized direction in the X and Y plane. Otherwise, if the imaginary part is non-zero, that means it is complex. In that case, exactly in tune with this Borden-Wolf definition, if it is complex, then you are having this helicity of the beam, and that you define like this. So sigma 0 means plane polarized light, sigma plus minus 1 for circularly polarized light, sigma any other value 0 to 1, you'll be having this in general standard elliptically polarized light. Now, so far as plane propagating waves or homogeneous waves are concerned, of course, you can recognize this P, the momentum density, which is E cross H, that is going to be along this direction of K. Okay, so the momentum will be carried in this direction of K. If you talk about the spin, that will depend on the helicity of the seam. It will be again direction of K. It will be parallel or anti-parallel to the direction of propagation, but it will be depending on the helicity. For right circular, left circular, it will be having different directions. If right circular beam is having this S in this positive K direction, the other one, left circular, will be having spin in the opposite direction. Okay. Now let's say you look at this vector waves and this optical current. That's I'm now moving to Michael Berry's paper, which is 2009, and I do say it's really a seminal paper. Now here some confusions are there. Students often make this kind of some gap is there. Let's say any quantity, electric field or magnetic field, they are real quantities. They are observables. You can measure them. They are observables. But the way what you do in mathematics, to use mathematics, what you do, you use this phasor notation. What you'll be doing? You'll be writing E as, let's say, half of, this is E to the power minus I omega t, and then plus E star e to the power plus I omega t. So what I'm doing basically, I'm writing the whole field, including the temporal thing, but I'm writing this, both these things together, and then I take the real part. So real part of that. So the real part is nothing but this plus this. That will be twice the real part of this quantity, twice the real part of this. I take half, I'll be getting the real part of this thing. So I'll be writing real part of this E to the power minus I omega t. Now you take this thing, pointing vector, P. Let's say I take this P will be writing it as E cross H. This again a purely real quantity. Okay? But in phasor notation, you'll be writing this 1/4 of E to the power minus I omega t plus complex conjugate, okay? And then cross, this is this vector. And then this H to the power minus I omega t plus complex conjugate. Now you take the product. Of course, you'll be having terms like this, minus 2I omega t, and then plus minus 2I omega t. You do the time averaging these quantities, because of quick oscillation, they go to 0. So you will be having only the cross term. The whole thing will be you're nothing but half of this is real part of E star cross H. That's the way you'll be writing everywhere. So that is what I've written down over here. Now you talk about something else, the D dot E term. D is complex and D dot E, the interaction part of the Hamiltonian or the light matter interaction. There also the same kind of thing happens. Here you can write it as some complex quantity phasor notation plus complex conjugate. And then E also will be writing like this. You'll be having again the same kind of combination, D star E and then D E star, that kind of thing. So just get used to that. This is the kind of notation you'll be using, but never ever think that we are dealing with actually complex fields. This is just for our notational advantage and mathematical advantage. Okay? Okay. Now what Berry did, he started off from this basic notion. He was looking at the pointing vector, and then you write it like E star cross H. Then you can ignore the coefficients I'm writing there. I'm using everywhere SI units. Some books, they use this CGS unit. Tarak was using CGS units. But people are most used to SI units. I'll be dealing things in SI units. But after some time, I'll be dropping all these coefficients which are there. By the way, all these derivations, there is some calculations and other things. I requested our student, Ghanasham, to prepare a brief write-up so that all the technical details, the mathematical details, derivations and everything, it is there. Ghanasham is here in the audience. If anybody has any question regarding this derivation of any formula or something, you can ask it, okay? And some of these calculations are not that trivial. It's not obvious. So you have to really sit down and do the calculation. It's uploaded on the website. Anytime you can download. You can download my lecture slides also, doesn't matter. So then what it does, he looks at the structure. H, of course, you can use Maxwell's equation. H you can write to one of the Maxwell-Karlovy equation. So once you do that, so you replace this H by Karlovy with these proper coefficients. And then you look at the structure of this quantity. You can break it up into two parts. One is this One is this E star cross del E. I'll come to that thing to explain this thing to you. And bold letters means vector. And sometimes I'll be using vectors with this vector notation on the top, sometimes with bold letters. Del operator is always a vector operator. So keep that in mind. It's a capital or bold letters or this thing with a vector sign on top. Sometimes I've written it without vector sign, but it's always a vector operator. And then other thing is you can write it as the imaginary part of E star cross E. This is a spin and orbital part. As I say, the derivation details Ghanshyam has in his notes, that is there uploaded. So you can break it up into these two parts. One is the orbital part, other one is the spin part. Okay. The main difference is that this has got no reference to the wave propagation aspects, whereas this one dependent on your system of reference. It can be intrinsic, it can be extrinsic. That Nirmalya discussed in great detail yesterday. So I don't want to highlight many of those aspects because already it was discussed in great detail. Okay. Now, here I need to comment about this operator del. It's not that straightforward thing. It is I call it for the time being, for the benefit of you, I'll call it the Berry's del operator. Okay. Because Berry extensively uses this operator in his paper. The meaning of this thing, this output of this quantity, this A nabla B, it is output is a vector, and the ith component of vector you'll be writing it as AJ, BJ, this thing. This you can write in terms of the direct product of two vectors to one vector operator, other one, and or you can write it as to the tensor product or direct product. That's your preference, which way you want to do it. Okay. As I said, this one creates some complications in derivations, so it is not the usual standard thing. So you get used to that. So this will be x component, for example. You'll be writing it ax, this j and j must be the same, the repeated index. So it will be sum over the repeated index, ax at bx, ay by, z at bz. But the operator here is always the same. Ith component will be depending on the ith derivative. Okay. So this is your del operator, which will be extensively used in all these studies. So now look at the structure of this thing. Look at the orbital part. If you really ask the question, what is the structure? I can treat it in the Dirac bracket notation. I can define a state vector where the three components of the field E, I can write it as three components of the electric field. Ex, Ey, Ez, I write it in a vector form. I'll be having this thing. In that case, I recognize this quantity. It can be easily recognized that it is the local expectation value of the momentum operator, momentum density operator, P. So this PR, you can recognize H cut, I set it to be equal to 0. So PR is just I times nabla. So you recognize this orbital part. It is purely connected to the local spatial variation of these quantities, and it definitely depends on your standard, which frame of reference you are using to define this quantity. So this is the meaning, physical meaning, and this is the direct connection to quantum mechanics. So there are a lot of papers depending on the quantum spinel effect and other things. So this is the basic notation they use. So this orbital part is treated as this local expectation value of the momentum operator. Whereas look at the other part, this spin part is slightly more complicated, which you are writing as imaginary part of E star cross E that you recognize as a spin, and del you recognize connected with the operator P. So you'll be writing a del of this operator, this ESE, and then so again A cross B, you can write it through the generator, which Bimalendu was discussing in one of these courses. So this S you recognize as the spin 1 particle operator. So this one you can recognize as the expectation value of the spin. So this next part, P spin, has total reference to the spin state of the particle. So you think about a right circularly polarized light or left circularly polarized light, they'll be carrying a spin in the direction of propagation, either parallel or anti-parallel to the system. So now with this understanding, the direct connection with this quantum mechanics, you can form a fully quantum mechanical kind of treatment, formal treatment. And otherwise, you can go on classically and calculate the things and extract the results. So what are we doing now? Giving some interpretation to all these quantities, P spin and P orbital. So let's now get into that business. Okay, now, by the way, this slide I showed, and when I wrote this slide, I could have done the same kind of exercise. Instead of writing H as curl of E, I could have written E as curl of H. So if I had done that, I'll be having the similar kind of thing, but everything will be expressed in terms of this magnetic field. So that is what Berry calls the electric magnetic democracy. So if you use this electric magnetic democracy, these things get little bit, you have to add the magnetic field components. So that's what we do here. So electric magnetic democracy. So you'll be writing in that case is 6 vector instead of 3 vector in standard R3. You'll be writing this 6 vector, not in Euclidean space, but in a complex. These quantities can be complex. So you'll be having the first 3 components of E and then 3 components of H, 6 vector. But still, you can talk about this orbital momentum and the spin momentum. You can break it up into the local expectation value of this thing with respect to the 6 vector. And spin also you can define again the same way that IP cross S, this thing. So you have this spin 1 operator and you can write it as expression value of the spin 1 operator. Okay. Next, what do we do now? Now include both this electric and magnetic thing. What this, as I said, that's the very called electric magnetic democracy. So we're using this thing, so you can write it full thing, this transverse, this spin and the orbital part, you can write it in terms of this orbital part. You have the 2 contribution coming from the electric field, coming from magnetic field. Of course, this magnetic field contribution would be smaller in standard scenarios, except for strongly magnetic systems. And PS you recognize as part of this spin angular momentum. And S you define as E star cross H, the electric contribution and the magnetic contribution. I'll show you this magnetic contribution plays a very important role when you try to decide what is the force acting on dipolar or more complicated particles. I'll come to that at a later stage. Okay, so with this goal, let us now try to look at the structure. Now I specialize to evanescent waves. I said the way you calculate, which I outlined, anybody can sit down for 10-15 minutes to derive all the expressions. You can calculate what is the structure of V. So now let's say I take a structure where the wave is propagating in the Z direction. So the surface is this is Z and this is your Y, and then X is the transverse direction. Okay, so surface is, this is the surface. So I'm talking about a wave which is a surface wave. It could be a waveguide mode, it could be a surface plasmon mode, it could be evanescent waves, doesn't matter. It is only details, there will be differences in details, but the character, generic character will remain the same. So I'm talking about an evanescent wave which is propagating in the Z direction, and it is this wave, total wave vector is a complex wave vector. So it decays in the X direction. So that means in the transverse plane it decays and then it propagates along the Z direction. And now if you look at this starting this vector, the field amplitude, it will be having X component, Y component, as well as a complex Z component. This is the crucial thing. There is a complex Z component there, and then purely imaginary Z component, and it depends on what is the transverse wave vector, which is purely imaginary. This kappa is purely imaginary. Okay, here this kappa is real, so the I kappa is purely imaginary. So the whole wave vector in this scenario is a complex wave vector. And M figures here, this M decides whether you are dealing with which helicity you are dealing with. So I'll come to that later. Okay, so now you can see that here this wave is, again, let me remind you, it is propagating along the Z direction and it is decaying along this, decaying along this X direction, and the structure of the vectorial structure of the wave is given by this. So it has all X, Y, and Z component. So this thing, and there is another main point here is that there is a 90-degree pi/2 phase difference between X and Z component. Now let me go back to simple scenario. Let's say you have a circularly polarized light. Why the wave is circularly polarized? You'll be writing the circularly polarized light. Let's say right circular polarization as X, this sum EXX, and then plus I. This is the X component and this is the Y component. So that's the way amplitude is the same. That's why it is a circularly polarized light. So if it is a right circularly polarized light, you'll be writing it like this. So now this tip of the vector, let's say this is my X direction, this is my Y direction. So one component is lagging behind by this factor pi/2. So that leads you to the rotation of the vector in this transverse plane. As the wave propagates in the Z direction, deeper in the board, the tip of the vector rotates in the clockwise direction. Now I have a similar scenario here. But now it is not in the xy plane, the rotation. Now it is rotation in the xz plane. There is again phase difference of I. That means now I'll be talking about wave is propagating in this direction. And that means I'm talking about the plane of incidence. My plane of incidence like this. This is z direction. This is my x direction. Now this component and this component, there is a phase difference of I between them. So the wave will be, tip of the vector will be rotating like this as it propagates. So the rotation is in the xz plane. The moment the field tip of the vector rotates in the xz plane, it creates a spin in the transverse direction. That's the physical origin of this transverse spin. Okay. So this rotation, again, the main crux of the matter is that there is a 90-degree phase difference between both the components in the xz plane. That means in the plane of incidence, and this rotation in the plane of incidence leads to the circulation of the vector in this tip of the vector in this xz plane. That leads to the genesis of the transverse spin. Now, once that is recognized, similar phenomena you can have in this other case also. You talk about a Gaussian beam. By the way, there's a classic paper they calls it the optical wheel. The things rotates as it propagates in the z direction in the xz plane. The ILO and others, Banger and others, they had a paper. I don't remember the year. Quite some time back in the initial days of the spin orbit photonics, they had a paper. They could show that this in the Gaussian beam also, because of the structuring of the beam, that is a Gaussian transverse distribution of the field. It has an analogous circulation of the field in the plane of incidence. And that also, again, you see the x component. So x component and z component, x component and z component, they are having this phase difference of pi by 2. And then that pi by 2 phase difference leads to the rotation, again in the xz plane, in the direction. Now we don't talk about plane of incidence because you are talking about a Gaussian beam. Any direction, any cross section you take of the beam, you'll seeing this phase difference between the x and z components. That will lead you to the rotation of the vector, field vector, and that will lead you to this transverse spin. So the feature is generic. It can be in Gaussian beam. It can be in this any other wave. We have given the examples only for two cases. One is the evanescent wave. Other one is the Gaussian beam. But I claim that this is generic phenomenon. Whenever you have in the transverse in the longitudinal direction, you generate a wave a field component which is complex, purely imaginary in character, so that it is different from the transverse components. You have this rotation of this kind of rotation in the plane of incidence, and hence you'll be having this generation of this transverse spin. So now we understand, yes.
So this can happen in non-paraxial beam.
Of course. Any generic case, non-paraxial beam, paraxial beam, it will be always there. The origin is this purely, as long as you have this purely imaginary component in the longitudinal direction. Right. That's true. Okay. So we move on. So I tried to summarize this thing. This is just like in elliptically polarized light in transverse plane, what happens, there is a phase lag between x and y component. Here also you have the phase lag between x and z component. This rotation, and that rotation leads to the rotation of the field vector, and rotation of the field vector leads to the generation of this transverse spin. Now there are very striking consequences. I'll try to concentrate on those striking consequences. Okay, let's start with the simplest possible case, the transverse spin. Let's now have a look what happens in case of what happened? It's stuck or so? Oh, no. It's lag. Okay, so let's now have a closer look at the expressions and then try to see, as I said, this wave vector now is complex. If you take the z component, having this thing z, kz is the z component of the wave vector. It has a transverse component which is purely imaginary, which is given by kappa. kappa is this, of course, this square plus this square has to end up with this k square. So k square will be kz square, and then I kappa square it will be minus kappa square. You took to the same side, so kz square must be equal to k square plus kappa square. So z component is going to be larger than the free space propagation vector, that is k is the omega by c, that is your free space propagation vector, it will be larger than that. That's one of the characteristic feature whenever you have the excitation of the evanescent waves. Evanescent wave component, in case of plasmons also, surface plasmon wave vector is larger than the incident wave vector. Okay, so now look at the structure of this orbital part, spin part. Let's first concentrate on the momentum. This is the momentum density. You see this orbital part or the canonical part is proportional to the real part of k. That means it is along the direction of propagation. So canonical momentum always is along the direction of propagation. Whereas the spin part, if you look at the momentum, it has two components. One is very simple, again, this along this direction of this thing. And of course, it is decided by what is the character of the wave vector. It is decided by this thing. So again, all the things are characterized by this part, but it has got no reference to the spin state, no reference to the polarization, the longitudinal part. But the transverse part, surprisingly, P spin has this transverse part which is proportional to the helicity. So the helicity you change, the spin momentum, transverse momentum is going to change its sign. So, and that gives you, again, remarkable possibility of the spin locking or the spin direction locking. You can control the way a surface plasmon will be excited if you control this state of the incident, state of the polarization of light, whether you choose the helicity. I choose a right circularly polarized light, I can excite the plasmon in the positive direction. If I choose a left helicity beam, then I'll be exciting the plasmon. I'll be going into the details in a later slide. The basic point here is mentioned here only. So the canonical part canonical part will be this thing, it's along this direction of k. Spin part has this component, which is the remarkable part, which is later I'll be connecting to the so-called, this is referred to the so-called Belinfante spin. The origin was in that 1940 paper. But if you look at the spin momentum, the spin angular momentum, it is again having this z component and y component. So it has a z component which depends on helicity, just like your circularly polarized light. Sigma will carry plus minus 1, it will be along this direction of propagation or opposite to the direction of propagation. Whereas there is a transverse part which depends on how damping, what is the damping factor. You remove the structure, that means you remove that wave is no longer evanescent. That means this kappa is going to be equal to 0. There is no kappa in that thing. Of course, this transverse part vanishes. So it's origin of this thing, the structuring of the beam. The structuring of the beam is the crux of the matter. It really decides whether you'll be developing a transverse component of the spin or not. So the moment you structure the beam, you may end up with this structure of spin, and there will be this thing. And by the way, this surprisingly enough, though spin is always connected to helicity and everything, the transverse spin, it is independent of the helicity. That's again gives you the basis for this spin momentum locking, because then in that case, the spin is independent of the helicity, but then it depends on this direction of propagation. You flip the direction of propagation, you'll be generating a spin in opposite direction. So that's what tells you that if you generate spin in opposite signs, that means you are with one polarization, you'll be exciting one wave, other case, you'll be exciting the wave in the other direction. Okay. If you have any questions, you can stop me, you can ask me questions. No. You look at this thing. It's real part cross imaginary part. It's perpendicular to k, perpendicular to the direction of propagation. This part, which is PS, has a part which is cross product with this real part of k. Real part of k gives you the direction of propagation, right? It's a cross product. Cross product means it is perpendicular to this cross product. You are talking about the first part? This is along this direction of propagation. No, see, this is that I already said that this one is the orbital part, which is straightforward, which is directly proportional to k. But this spin contribution, there could be this thing, there could be a part along this direction of propagation, and then there will be a part which is perpendicular to the direction of propagation. The part which is perpendicular to the direction of propagation is helicity dependent. No, I didn't ask the question, answer, get the question. Ah, right. 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 Okay.
This spin momentum locking, where you're saying that spin direction, what way it is different from the spin all?
Oh, a big difference. Phenol is basically a orbital angular momentum getting transferred into the spin momentum. That's what Nirmalya discussed yesterday. But this is quite, I'll come to that later. Just a minute. Yeah. It's all purely orbital effect. Okay. Okay, so we move on. So this is the actual this dependence on this sigma and the dependence on the direction of propagation we have to remember to some extent. Else I'll come back to this slide later. And the main character you have to remember in case of evanescent wave, you have this structure. This total wave vector is a purely complex kind of character. Now I move on to transverse spin and then nature and consequences. The transverse spin we saw. This part, I'm looking at only the transverse part of the spin. It is not the longitudinal part. I'm not looking at this longitudinal, the sigma dependent part. I'm looking at the transverse part. So the transverse part is real part of k cross imaginary part of k divided by real part of k square. And you translate it in simple language in our geometry. It is kappa divided by kz, and this it is directed along this y direction. Is a perpendicular to the plane of incidence. Now look at this. Of course, it depends on the direction of propagation, kz. What is the direction of propagation? If you flip the direction of propagation, the transverse spin is going to flip its sign. Let's clearly picture this. Picture is taken from one of Bloch's paper, and one of Bloch. I cited all these papers at one slide, so I'm not separately putting them in the different things. So the wave is propagating in this direction. It will create this thing. So these waves are evanescent here. So because of this evanescent character of the wave, we'll be creating a transverse spin in this direction. Okay, you flip this direction, this kz, it will be this spin will be pointing in the opposite direction. Surprisingly, this kind of transverse spin can exist even for TE and TM. It does not carry any helicity. It need not carry any, because this TE and TM, TE means what? You can take this m to be infinity, you will be ending up with this TE polarization. Look at the original expression, 1 plus m x plus m sigma times m divided by square root of 1 plus m square. You'll be ending up with this. Even those waves, the TE and TM also will be having normal to XY plane, there will be this transverse spin effect. So even the standard surface plasmons or something, they carry this thing even for TE incidence or TM incidence, not that circular polarization incidence has to be there. So a generic feature of structured light, as I said earlier also, is imaginary longitudinal field component that is the source of this transverse spin. And as I said, this all because of rotation in the XZ plane, the rotation in the plane of incidence. This is again a picture from Bloch's paper, as I said. And now we move on to more details of this spin momentum locking. Yes. Huh? Previous slide. If you don't have structured light, kappa is 0. But you would be able to structure if you structure finally what matters is the structure of the electromagnetic field. That is what I need to bother about. I don't worry about how the structure is prepared. The field what you generate, that has to have a structure.
Yeah, exactly. So if you now
Huh. Gaussian beam already has a structure.
Yes. You consider that. Now you reflect this light on the way. And that would also be
Yes.
that is what we often have.
Yes, yes, yes.
So is there a way to really reflect these types of either through the beam itself or through
Yeah, I understand. So I think you can do it in many ways. You can do it in many ways. You can lead to a final target is that you have to have a thing which is structured, and because of this structuring, you can generate this thing. The main thing, target, as I say, mathematically speaking, you have to have a longitudinal component which is purely imaginary in character. The moment you generate that, by which means I don't care, by which structure I don't care, but if you have that thing, you'll be having this transverse speed. No, no, that is an example. This is one simple example. You can do the algebra, you can do all the mathematics, you can show clearly, okay, this component is along x direction, this is along z direction. You can show that. You can do it for any vector beam also. In many of our papers, we have done the calculation with vector beams, okay? And with those vector beams, of course, you can't do this kind of simple algebra. With the Laguerre-Gaussian beam and vector beams, we have done that exercise, okay? Okay, so next thing what do we do? Let us now look at the spin momentum locking. So of course, we understood that this transverse SAM, transverse spin angular momentum, that depends on the direction of propagation, whether this kg is positive or kg is negative. Okay, of course, the surface plasmon can be there. There can be waveguide modes. As Pavan was asking, you can generate it by many other methods. There are several papers where they talk about the interference of counter-propagating waves. Bleok has several papers like that. In many other systems also, they generated this kind of thing. We also looked at many different geometries. I'll give some examples if I come to our work. So if I come to that part, I'll give some details on that. Once you do that, of course, this I can have a situation with the surface plasmons or waveguide modes I can excite where I have a transverse decay or transverse structuring of the beam that will carry this transverse spin angular momentum. And then, of course, here I need to recognize the fact that this TSAM is attached to the propagation direction. So, and then you can have this quantum spin-Hall effect and spin momentum locking. What is this? The basis of this thing, let's say you can think about a very generic kind of experiment. And the generic experiment is that you take a circularly polarized light. Of course, the circularly polarized light carries this ±1 sigma helicity. That means along this direction of propagation or opposite to the anti-parallel to the direction of propagation. So this incident light will be having a helicity dependent polarization, which will be along this positive y direction or this negative y direction. It will create this transverse spin like this. And now I can have this spin transferred to a surface wave through a scatterer. So let's say I can have a dipole scatterer, I can have any other kind of scatterer. The first experiment they did in this Zayas screw, that was with a groove. A single slit was there. I'll come to that experiment later. I can have a nanosphere, I can have any other scatterer, any inhomogeneity on the surface that can do the scattering. It can translate the spin to the surface mode. So opposite spin states will excite this SPs in the opposite direction. That's the spirit here. So if you have wave is propagating in this direction, spin state will be, or this coming with the helicity, which is having the positive, this sigma positive and sigma negative, they'll be having in different direction. So I'm coming in with this light with this right circular or left circular, that will be transferred to the surface mode via the scatterer. It will generate, depending on this thing, it will be going, this surface mode will be going either in the positive direction or in the negative direction. That's a simple idea of the spin momentum or the quantum spin-Hall effect of light. Now, let us now have a look what really happens in real experiments and how one can really translate this thing into an experimental scenario. So let us now talk about this thing, the spin direction coupling. As I said, this is that classic paper, 2013 paper. So here I need to just tell you one thing. I need to understand how this, let's say here they're talking about dipole scatter. There's a dipole. This dipole has only two components. One is the z component. One is the z component, other one is the x component. It doesn't have any component along this y direction. And this kind of dipoles you can excite by sending a circularly polarized light almost at grazing incidence. So almost near the surface, you send a light, it will be polarizing the dipole either is right circular polarization or the left circular polarization. If you do that, this HY, what I've written down is HY, it is just the Fourier image, Fourier transform of this H, which is, you can write H as a function of Kx, X and Y. So you are doing a Fourier transform, H, X, Y. I'm not writing this thing, so it is integral, this dkx e to the power I kxx and H, Hy, Hz, this is this thing, Hy, this kxx, Hy, kz, and then x, this kz, kzz, okay, I kz, and then this is z, okay, or I've written it down there, okay. So I'm writing it I kz z, and then kz, and then this is kx, and then z, okay. So this is your transform. I'm looking at the Fourier spectra. So that's what I've written down here. That is what I've written down over here. So if you look at this, you can, this both the dipoles, z-oriented and x-oriented dipoles will be contributing to that. And this is the thing. Now let me tell you one thing, a z-oriented dipole can never emit in the far field. So of course there will be some far field radiation from this dipole and the near field radiation or near field pattern. So if you look at the far field thing, of course the z-oriented dipole can never emit in the z direction. That is clear because for z orientation, this there is no x component, the kx is equal to 0. So this part doesn't contribute at all. Now, if you talk about near field, of course this kx and kg, they are not, one of them is purely imaginary. So this quantity is going to be purely imaginary with a plus or minus sign depending on the direction of propagation. So now everything matters how these two contributions they interfere. So there is a destructive interference and there is a constructive interference. To understand that, I need to understand how this spatial component, spatial Fourier component depends on this, what is the symmetry aspects of this part and the symmetry aspect of this part in the context of when I flip this x to minus x or kx to minus kx, okay? So now I go to that slide, next slide, where this is more clearly explained. So let's now have a look. I'm plotting up everything, this spatial Fourier component as a function of ratio of this kx by k0. So if I take this positive direction, this is kx positive direction, kx is negative direction. These boundaries, kx is equal to k0, that gives you the light line. So kx in modulus less than k0, that is within the light line, within the light cone. And if you take this kx larger than k0, that means beyond this 1 plus and minus 1, it's outside the light line. That means within kx k0, within minus 1 to 1, waves are propagating, and outside the waves are evanescent. So now I have to decide what is the character of interference inside this light cone and outside this light cone. Inside this light cone, as I say, both this kx and kg, they are real. You don't have to any problems. This kx and kg are real. But if you have this outside the light cone, this kg can be purely imaginary because kg will be writing as k square minus kx square. Okay, and k square minus kx square. That means that is going to be larger than is positive thing. It will be outside this light cone. So the waves will be evanescent right over here, there. And in this domain, you can either excite these different kinds of modes. You can take a waveguide structure. You'll be having this green line where this waveguide mode will be excited for this positive value of kx or this negative value of kx. And this red line is for surface plasmon. Again, when you have this thing, this kx is satisfies kx by k naught is equal to the surface plasmon wave vector, you'll be exciting the surface plasmon, both either in the positive x direction or in the negative x direction. Okay. Now look at the symmetry of this thing. Px and Pz are odd and even parity with respect to this thing. That's clear. So if you have this kx positive and then kx negative, this one flip sign, whereas this Px doesn't flip sign. And this minus and plus sign depends on whether you are looking at the fields above the dipole or below the dipole. Okay. That is very clear because the dipoles have to radiate and the radiation away from the dipole is bound to damp. That's the reason you have to ensure that infinity there is no excitation. So that the field damps away. So you can talk about the far field radiation pattern. We will be having purely transverse character of the waves, which is IKR by R, that kind of dependence. Else near field, there will be some this thing. Now, what I try to point out here, this interference can be destructive on the positive kx side, and interference can be constructive in this negative kx side. So here you see the the constructive interference, and here you have this destructive interference. And you can maximize this destructive interference instead of this right circularly polarized light. If you take this elliptically polarized light, you can make this quantity. Black solid line is for right circularly polarized light, and dashed line is for this the elliptically right circularly polarized elliptically polarized light. You can make this quantity 0. So main point is that you create an asymmetry in the positive x direction and this negative x direction. That means in one direction it will be having the propagation of the wave, other direction it will be nullified. It won't be propagating. So that's precisely the experiment they did in Zayas group. And what they did, yes, any question? Okay. So what they did is the following: they mimic this dipole by this. Let's say they put a dipole over here, some molecule or something. I don't remember. They didn't give the details or something. And this group was mimicking the situation where you have the scatterer. This group will be a scatterer. This will be behave like this, and then you have a right circularly polarized light. You will be creating the right SPP or this left SPP. So you look at this thing. So you can change the polarization of state of light by this lambda by 4 plates, orientation of this lambda by 4 plates, which Nirmalya discussed at great length yesterday. You can move you can change the character of the light from this left circular to right circular to left circular. And in one case, you see when you choose this linearly polarized light. Oh, this picture is not showing. I don't know why. You can see the picture, right? Let me just say in words that if you take this linearly polarized light, which is the equal superposition of right and left circular, you will see the equal spots on the left and right side. So there is equal probability that wave can propagate in the positive direction and the negative direction. Now, preferentially, you take left circularly polarized light. You'll be exciting this in one direction. For this one left SPP, you'll be having exciting in one direction. Wave will be propagating preferentially in the left direction. Another case, wave will be propagating in this right SPP, right direction. Thus, philosophy is like this. So you excite both the dipoles, X and Z oriented dipoles, and it is interference not only in the far field. It is interference. This effect is because of the interfering effects, destructive and constructive interference in the near field. And the near field interference leads to the fact that it will preferentially choose one direction, and the wave will be propagating in this thing. And the state of direction of the excitation of the surface plasmon, or this thing on the surface, that will be decided by the incident state of polarization. That information about the incident state of polarization is carried to the surface by means of the scattering, by a nanoparticle, by a group like this, by any other mechanism, any inhomogeneity on the surface. Yes. Good question. Yeah. Yeah. So see, both this Px and Pz, they are having the same symmetry. Pz symmetry is obvious. Pz is pointing this way, X this way, that way, doesn't matter. Px is slightly more tricky. Px, when you flip from X from plus to minus, Px will flip sign, right? But that is compensated by the temporal factor. I omega t take pi, then it is the same thing. So the Px also is not affected by the X to minus X. It will preserve singularity. So what you are worried about now, overall effect, the field what is created by this thing, whether they are symmetric or anti-symmetric. That's what matters. That's the reason what it decides. In near field, you can have this interference on one side, constructive interference, other side, destructive interference. That preferential choice that decides which way the wave will be excited. Yes. I don't know. I haven't seen any paper. There should be something, of course. Oh, I have never seen those papers. Otherwise, I would have highlighted some of that. Okay. Which group is that? Nirmalya? Oh, I see. Okay, so we move on to more exciting things and surprising things. Okay. So this is so far as this surface, the spin direction locking is concerned. Now let us concentrate on the momentum, spin momentum and this orbital angular momentum. So first look at the canonical part, orbital part. Okay, if you look at the structure of the canonical part, again the Berry operator is there, Del operator is there. You can calculate for this evanescent waves, which you have in case of total internal reflection. You'll be writing it like this, okay? It will be, you can write it, going along this positive k direction. Real part of k depends on that will decide what is canonical momentum, what will be there. So of course, this is related to the gradient of phases of electric and magnetic field, that is clear. It's all related to the Del operator, so it is a gradient interface associated with local wave vector, because you remember that is local expectation value of the momentum operator. So that's how it's very easy to understand what is the origin of this term, what is the interpretation of this term. But things are not that simple in case of this other spin momentum. Let's look at the structure of the spin momentum. There, the structure of this S, already we saw that there are going to be transverse components, S. So spin momentum will be depending on this thing. So you can calculate. There will be a Y component, which is the transverse component. Other one is the Z component. Z component again depends on the structuring of the beam. It depends on how the wave decays. This kappa is there. And then of course it's proportional to kappa. As I said, all these calculation details are there in Ghanshyam's notes. You can look at that. You can ask him questions also if you get stuck with this thing. So this thing that this this total spin momentum, it will be having two components. One is due to the canonical, one is due to the canonical part. Other one is the transverse part. And this transverse part is the one which is truly enigmatic. In what sense? So enigmatic in one sense, it is you have a situation you generate by this transverse spin is there, transverse spin momentum is there. And that is what you call the Belinfante's momentum. As I said, this is the classic paper by 1940, which is, as I said, it's a very, very difficult paper. At least for me, it was a difficult paper. And I still don't understand, as I said, all of it. But the crux of the matter, I do understand. So that's what I'm trying to tell you, that there will be a transverse spin, and the transverse spin is going to be helicity dependent. That's the crux of the matter. You have a spin component, which is transverse, and it depends, it senses the helicity of the incident light, whether it is right circular, left circular, which way it is polarized, right polarized or left polarized. Now, once that is the case, then he called it, he said that this generated by the intrinsic SAM. All this spin angular momentum is always intrinsic. Nirmalya also mentioning yesterday, because there is nothing extrinsic in this problem. So it cannot be associated with the propagation effects. And the one other thing is that the P spin, the structure is curl of something. You know, the divergence of curl is always 0. So this divergence of this spin momentum is also going to be 0. The field is solenoidal. And the moment the field is solenoidal, you know, it cannot carry any energy along its direction of propagation. Okay. So this spin momentum, it cannot carry any energy. That's another lesson we learned, because of the structure of this divergence of curl is 0. So the divergence of spin is 0. It cannot have any source. So it doesn't carry any energy. There is no energy transport in this thing. So Belinfante argues that it cannot carry any energy. Let us see now. We can make this transverse spin exert any force on a dipolar particle. So that calculation is much more tough. Okay, I'll come to the details, little bit details, but that some of the part of the paper we didn't work out. I leave it to the students to work it out, but the paper is there. You can go back to this very nice paper by Nieto Vesperinus and others. So you look into that paper, you understand how complicated the scenario is. Okay. So the argument is that if you want to have any spin information about the structure, then of course you need to look at the SAM. So it's the primary quantity you can think about. Whereas you talk about the transverse spin, the spin momentum, this Belinfante momentum, that quantity still, since it is having this enigmatic character, you call it basically, at least Belinfante used to call it virtual quantity. You can't directly, he used to believe that it cannot be measured. Okay. So that is the next point. So you look at the force on a dipole. Now you calculate the force on a dipole, you know, in electrostatic, the way you do it is P nabla acting on E, the variation of E. So if you have a structured field or E is structured, then P nabla, it generates some non-zero effect, and P nabla E will create a force which will be exerting this. So that means by by structuring the field or structuring this thing as in tweezers or something, you can make the particle feel some force, which can keep the particle in place in an optical tweezer. Owen will talk about that in his whole lecture, right? Okay, so he has got a lot of experiments and theory on that, so he will be talking about that. So I'm not getting into those details, but I'm just trying to point out what are the actual scenarios. And this is the thing, you calculate this P nabla, but now this nabla is again a Berry operator. So you need to little bit careful to calculate. And this WE is the energy density, electric energy density. WM is the magnetic energy density. You recognize them as epsilon E mod square and this mu H mod square. That is the WE and WM, energy density of in the electric and the magnetic field components. So if you work it out, you learn that there are two parts. One is the first part. Of course, it depends on the spatial variation of the energy density, which gives you the so-called this gradient force, which is quite familiar in the scenario of this optical tweezers. Okay, and second part, of course, you recognize is the canonical momentum, the force it can exert, and this canonical momentum exerts this force. But lo and behold, there is no reference in this force to the spin momentum. So it just doesn't appear in this force expression on the dipolar particle. The spin momentum doesn't figure, and hence Belinfante believed that this thing is not measurable. It is an elusive quantity. In order to retain the mathematical structure, mathematical integrity, you need to assume that this is bound to exist, but at the same time you can't measure it. So he used to call it, all through his paper, he used to call it this Belinfante momentum to be an elusive quantity. Okay, not observable in dipolar light matter interaction. So that is the consequence. Now, is the situation so bad that is it that there is something mathematically exists, we can never measure it? The answer is very optimistic that it's not that. There is a way out, and the way out, again, I don't understand completely one statement. I was discussing with Nirmalya this morning or yesterday, right? So I still don't have the answer. Maybe one of you know the answer, but you can give me the answer. So here, this kind of meeting is good that I can clear my own doubts if from input from the participating people, okay, or learn few things, those things. If anybody can illuminate on those points. So what is that? So then you look at this thing. You look again this. You want to measure this helicity dependent momentum. So Belinfante momentum you can observe in this interaction of electric and magnetic dipoles. There's a striking fact. Even if you take a non-magnetic material, that mu is equal to 1. Even in that case, you do a mu, that mathematical part we understand. You can have a magnetic polarization distribution, polarizability distribution. You do a mu expansion. You know this mu expansion you write it in the basis, this spherical harmonic basis, the vector spherical harmonics is pretty complicated. See, the point here is that when you go to the spheres on this me scattering problem, in general, you are used to all this spatial harmonics, YLM, theta phi, all those functions, you know, in the context of the scalar problem, scalar hydrogen problem. You know that. You deal with this YLM, theta phi, those functions e to the power Im phi in the context of scalar functions. But if you talk about a vector scattering problem, actual rigorous vector scattering problem, that was due to Gustav Mie way back in 1905 in the same journal, same just took physics, where this Einstein had the seminal paper, 1905 paper. This result was there in the same paper. So he worked out this theory, rigorous theory. There is no approximation, nothing. He showed that you can do the expansion in the so-called this vector spherical harmonics. You can calculate. So each component x, y, z are theta phi component in the spherical system. They are functions of this YLM theta phi. At the same time, you can distinguish between two classes of solutions. In one case, the radial component of the electric field will be absent. We used to call them the transverse electric, but it's not our usual transverse electric. In other case, radial component of the magnetic field will be absent. In that case, you call them the transverse magnetic fields. So you can design the problem in terms of this vector spherical harmonics. Here also the same story. You have you want to calculate the magnetic polarizability. You do a general mu expansion. You will see that even for case mu is equal to 1, they'll be originating from this higher order mu series in the mu series. This is the non-magnesian thing. So for the time being, you can assume that both this electric polarizability and magnetic polarizability, they are not zero. Now again, you calculate the force. By the way, this I gave the reference in the previous slide. This is the Optics Express paper 2010 by the Nath and others. It's a very classic paper. And I strongly advise the students to go through this paper to work out the steps. We did some, but then we didn't complete the story. There was no time. And you can calculate what is this change in the force because it's electric magnetic interaction, electric and magnetic interaction. It turns out that this force has a reference to the total pointing vector. Pointing vector, total momentum density of the pointing vector. The moment it contains this total pointing vector, of course, it has the spin part, it has the orbital part. So the spin momentum also plays a role in this thing. So that's how it can be discernible in the interaction with the electric and magnetic particles. And that was the experiment done by the Riken group. I'll give some details about that experiment. And there, I think I'll move on to something what we did over the years. Okay, so how much time I have?
It's about time.
9:30 I started. It's about time. Okay, fine. I'm almost at the end, no problem. Okay, so this force is transverse to this gradient and radiation force. This, canonical momentum has this gradient and radiation force that I showed you earlier. And this is proportional to this thing. If you assume that this imaginary part, these are real quantities, there is no absorption in the medium, you can assume both these quantities to be real. In that case, imaginary part is 0. And once the imaginary part is 0, this force is going to be, P spin is going to be along the direction y. So it will be a transverse force. So this transverse spin momentum will exert a transverse force. And that was calculated, that was proven in another, and that's how this, you can look at this elusive Belinfante spin and you can check the character whether it's truly helicity dependent or not. So the experiment was done in 2016. It's a Nature article. I just summarize this result, and there I think I'll end the thing. I won't get into my own research or something. That's not important. It's a tutorial lecture. So this experiment is like this. There are two laser beams were used. One is 561, the green laser. Other one is 660, which is a red laser. And this red laser was the actual beam which created the spin and the transverse spin and all these other effects. And the green laser was used just to monitor the shift of this thing. The very first thing they did, they made a nano cantilever. This nano cantilever was able to give a resolution of femtonewton. The resolution scale of this nano cantilever was this femtonewton. So any small displacement here of this nano cantilever could be measured by this. So this green laser beam was deflected by this nano cantilever and was falling on a quadrant detector. Gopal can give you more details on those quadrant detectors. They use it regularly in their lab. Okay. So, and that's how they could know what is the displacement, what is the force acting on these particles. And the basic idea was that red laser was used to totally internally reflected on the bottom of this nano cantilever. That's how they were creating an evanescent wave. And the picture is like that. If this canonical momentum will be going the same way, so the canonical momentum is along the direction of the surface mode. And if you have a transverse spin momentum, it will be in the transverse direction. And the spin momentum will be depending on the helicity. So they measured what is the canonical force, what is the canonical displacement, canonical force along the direction of propagation, what is the transverse thing. So the longitudinal part, they could see that there is no dependence on helicity. And the polarization state of the incident light, which was controlling all this momentum, they were changing from quarter wave plate from -45 degree to +45 degree. So right circular polarization they'll be having at -45 degree, left circular +45 degree. So when they changed the state of polarization from right to left circular, there was no change in the direction of this force, which was acting in the longitudinal direction. So this is the canonical contribution, which is insensitive to the spin, whereas they looked at the transverse component. This transverse component, they changed from right circular to left circular, it changes directions. So look at the values. It is 0.8 piconewton. So that's the kind of force you have. That's the kind of force you need to measure. That's the kind of accuracy you need to have in order to go for this kind of thing. Initially, this picture was very pessimistic in the sense that okay, if I have to talk about this Belinfante spin and spin momentum, I have to measure them. I need to be having a super sophisticated equipment. It took them 3 years to develop the nano cantilever and to develop that experiment in Riken. But finally, they achieved that. It was in collaboration with some UK group. That's a different story. But they could do that, they could do this thing. But now there are other proposals with this focused beam and focused particle coupling through nanoparticles or something. They were able to measure this transverse spin in many other experiments. One might be having something in his arsenal to talk about this transverse spin in our optical tweezer systems in ICER. Okay. With that, I'll end. I'll take your questions if you have.